So welcome everyone to another LEAP seminar. Today we have Jonathan Hollar connected via Zoom. Fortunately, he could not be here in person. So just a brief introduction. Jonathan, it was a previous member of BABAR and FP 420 collaborations, but joined CMS collaboration in 2008. In 2015, he finally joined LEAP group, CMS LEAP group, as an assistant researcher. And since then, he was deputy project manager of the CMS fourth proton detector. However, today he will focus about the new CMS results on top quarks and other things from photon collision. So please go ahead, Jonathan, whenever you want.
Okay, thanks for the invitation, and I'm sorry I couldn't be there in person. I also apologize in advance for the coughing, so I think I caught a little bit of a cold, but hopefully my voice will last until the end. So yeah, as the title says, today I'll discuss some new CMS results on specifically top quarks, but also at the end a few other things from high energy photon collisions at the LHC. So as everyone knows, the LHC is the Large Hadron Collider, so it collides protons or sometimes heavy ions. And mainly the interactions come about via quarks or gluons, which sometimes produce interesting high mass things. So top quarks, W and Z bosons, Higgs particles, possible new physics beyond the standard model particles. So this is just an illustration of a standard TTbar event seen in the CMS detector in normal collisions. However, in these types of collisions, there's also always a lot of other stuff produced in association with the particles that we're actually interested in. So there's this well-known picture showing all of the effects of proton remnants, multi-parton interactions, initial final state radiation. So a lot of other things are going on in addition to the TTbar production, which means that in general, in this case, the exact amount of energy event by event going into the interaction of the quarks or gluons is not really known at a hadron collider, in contrast to an E plus E minus collider, where everything is very well specified in terms of the center of mass energy. However, in rare cases, even at a hadron collider, sometimes something else can happen. So the protons or ions are electrically charged particles, which means they can, in principle, stay intact and radiate off high energy photons, and then the two photons collide to produce something in the central system. So thanks to the huge energy at the LHC, for the first time, we have colliding photons at high enough energies to also produce some of the things mentioned on the previous slide. So top quarks, W and Z particles, Higgs, or new particles up to hundreds of GeV or even higher. And so in this case, it's kind of special since in principle, all of the collision energy of the two photons can go into the TTbar or whatever else is produced. And between that and the two intact protons, you have the entire collision energy of 13 TeV or 13.6 as it is now. All right. So just to briefly mention a couple of the different ways of studying two photon collisions at the LHC. I'm mostly going to focus today on the option to the right, mostly since it's the one I'm more familiar with and we're more active in the LIP CMS group, is using proton-proton collisions, where we use 4 detectors to try to tag these intact protons and identify two photon collisions. So the advantages here are that you have the highest possible LHC energies. Most of the time at the LHC is spent running proton-proton collisions, so you can integrate the maximum luminosity. Also, you can, with these special detectors, reconstruct the outgoing protons to tag these kinds of events. The drawbacks are that the photon fluxes off the protons are not so huge, especially at lower masses. And we also have to fight against this huge pileup effect at the LHC, where there can be currently up to on the order of 50 collisions happening almost simultaneously and overlapping in a single bunch crossing. The other road to doing this that's done at CMS and Atlas and others is looking at heavy ion collisions. So here it's a bit the opposite situation. So there's this huge enhancement from the atomic weight to the photon flux, which helps. The heavy ion collisions are also normally done at very low pileup, so the rate of multiple collisions in the same bunch crossing is low. The drawbacks are that the center of mass energy is lower, the amount of ion running time at the LHC is less, and it's not possible, at least with any current technologies, to detect the intact ions that are outgoing. So in this sense, the two approaches are actually highly complementary to studying two photon collisions in two different ways. So this is just briefly illustrated visually on slide 7. So from this paper reviewing two photon physics in heavy ion collisions. So note that this is on a log axis, so it's exaggerating a bit the low mass part. But basically, there are a few interesting features here. So if you look at for an assumed 1-year LHC running scenario, the black line from photon collisions from heavy ions starts off much larger than the protons in red at low mass, but then falls much more steeply. So in this particular scenario, at about 20 GeV of energy, it's actually below the what you get from proton-proton collisions and continues falling. And then at about 200 to 300 GeV is the area where we can start to detect the scattered protons in PP collisions and fully reconstruct these very high energy two photon collisions. So in that sense, it means the heavy ion approach is kind of ideal for low mass standard model cross sections and looking for very light beyond standard model physics. While the high mass proton-proton program with tagging is ideal for looking for very heavy final states like top quarks and searching for heavy beyond standard model physics. So as I said, for the rest of this talk, I'm mainly going to focus on the proton-proton case. So this one here at hundreds of GeV. All right, so just very briefly in 2 slides, how do we detect these two photon collisions with the outgoing protons? So as you probably know, the LIP group is involved in these small forward detectors at CMS, also at Atlas, I think, for detecting forward scattered protons at very low angles. So these detectors actually sit inside of the LHC tunnel about 200 meters away from the CMS interaction point. And when the protons come out of CMS and pass through this 200 meters, they're bent along the way by the magnetic fields of the LHC accelerator, which allows us to then swim them backwards and reconstruct the kinematics at the interaction point. So particularly the fractional momentum loss that we always call by this psi variable. And so in the case when both of the protons are detected, then the system is closed and the invariant mass and the rapidity of whatever is produced in the central system can also be reconstructed from the protons via the expressions at the lower right here. And so this means in principle, we can reconstruct the entire 13 TeV collision energy. Right. So that's all I'll say on the detectors. Then just to briefly say, of course, before we start looking for new and exotic things like top quarks and other beyond standard model physics, we want to know if we can use this technique to detect the expected standard model processes. So kind of our typical standard candle is production of dimuons or dielectrons from two photon collisions with at least one of the outgoing protons detected. And so that has been done in CMS first with the 2016 data and then more recently updated with the full run to data from 2017 and 18, and one sees we can indeed find a large peak for these standard model processes with dilepton invariant masses above 100 GeV, essentially, which gives some confidence that we can actually detect what we think we're detecting, and also gives a lot of constraints to quantify the systematics due to any leftover data and simulation differences in the scale or the resolution. So this is just one example. Of course, there are a lot of other validations and calibrations performed with other data control samples like elastic scattering or central diffraction and other things that are basically in the backup slides. All right. So that's just the preamble on the detectors and validation of that we can actually detect these very high energy 2-photon collisions. So now I'll turn to a fairly recent CMS result that is doing a first search for top quarks from colliding photons in this way. And so this is something that had a large contribution from current and former LIB group members, including Matteo Pisano and others. So basically, in terms of this exclusive TTbar process, there have been no other searches done at any type of collider at any energy ever, as far as we can tell. So of the different ways you could possibly produce this final state, the one on the left is the diagram we're interested in, with the 2-photon collisions producing a TTbar pair. This is a quite small cross-section, so less than 1 inverse femtobarn, although if we're able to collect on the order of 100 inverse femtobarns or more at the LHC, it starts to become more interesting. In principle, it's also possible to produce this final state through the more complicated diagram on the right, where multiple gluons are exchanged in the leading order. From the theoretical estimates, we expect this is very highly suppressed at high masses for various reasons. So in the analysis, we essentially treat this as negligible compared to the 2-photon production. So even though this is supposed to be very small in the standard model, it's still interesting to look for, partly because it's never been looked for before, but also because there are various beyond standard model scenarios that predict large enhancements to this process. So things with anomalous top quark electric or magnetic moments, effective field theories and anomalous couplings, extra dimensions models, and various others. So in terms of the data and event selection, this analysis is using about 30 inverse femtobarns of data that was collected during the 2017 run of the LHC. So there are actually basically 2 parallel analyses that are done depending on the final state of the top quarks. So there's a dilepton final state in which both W's from the top decay go to leptons, in our case, either electrons or muons. And then also the lepton plus jets case, where only one of the W's decays to leptons, and on the other side, you have jets. So these are basically analyzed separately and then statistically combined at the end to get the final limit. So this is just a brief overview of the event selection used for these 2 states. So in the dilepton case, both of these are basically fairly standard CMS top quark selections. In the dilepton case, they ask for at least 2 leptons, electrons or muons that pass standard momentum, eta, and ID requirements. At least 2 jets passing the B tagging with one of these fancy deep learning secondary vertex algorithms to identify the B jets, and 1 tag proton on each side of CMS. In the lepton plus jets case, it's similar. So they ask for exactly 1 lepton, an electron or a muon passing the standard ID and kinematic requirements. Again, at least 2 B tag jets. And in this case, they also ask for at least 2 light quark jets from the hadronic decay of the W. And again, one tag proton on each side of CMS. Then just going to one step beyond that, in the lepton plus jets case, there's also this clever idea applied of performing a kinematic fit to the TTbar final state to improve the reconstructed mass resolution. So essentially, the approach here is to allow the three momenta of all the final state particles to float within some reasonable range and try to fit for the best solution that satisfies several fundamental constraints on the overall momentum conservation, that the decay products of the W and the top are compatible with the invariant mass of the W and the top quark, and that the invariant mass matching between the protons and the top quarks is compatible. And so the effect of this is shown in signal simulation on the right. So the blue histogram is what you have before the kinematic fit with the standard reconstruction, which is slightly shifted to the left and fairly broad. And then after the kinematic fit, you have a significant improvement in the resolution for the signal events. And I'll come back to it later, but also the chi-square quality of the fit can be used as a further discriminating variable in the final analysis. So in terms of the backgrounds, the main background we're concerned with in this analysis, and really all analyses of this type, is a type of combinatorial background, because the LHC produces this huge number of almost simultaneous pileup collisions in the same bunch crossing. So this is just a cartoon diagram on the left of what can happen. So if you imagine each star is one collision within the bunch, you have one that's producing a real top anti-top pair through a standard quark or gluon production mechanism. And then you have two protons in the event, but these are coming from completely different collisions from the one that's producing the top quark. So this obviously can fake the same signal of two top quarks and two protons. So the basic approach to modeling these backgrounds is using a data-driven technique of event mixing. So the idea is to build a sample of real protons from data with a loose, non-overlapping event selection, and then combine these by mixing with the simulated background samples to build up a model of what these combinatorial pileup backgrounds should look like. And this, of course, also has to be accounted for in the signal efficiency, which is affected by the presence of extra pileup from protons. And so after this, it's checked in all of the main discriminating variables that this gives a good description of the distributions, in particular here for the proton Xi distribution in the final selection, where the light blue TTbar is this event mixing background prediction, and the black points are from the data. Okay. So then in terms of further discriminating variables, so in each of these two channels, the final signal extraction is done using a multivariate approach based on boosted decision trees. So in both of these channels, there are quite a number of variables used, something like 10 to 15. Just to note a few of the more notable ones in the lepton plus jets channel. Among the more powerful are the chi-square of this kinematic fit described in previous slides, the mass and rapidity reconstructed from the protons, and the multiplicity of the number of light jets in the event. And so in each histogram here, this is the data points in black compared to the background model from this event mixing method to verify that the inputs to the BDT are well modeled. In the dilepton case, it's essentially the mass and rapidity reconstructed for the TTbar pair, the mass and rapidity reconstructed from the protons, And also the angular separation of the two leptons is quite a powerful variable. And again, this is compared to the background prediction. Okay. So then coming toward the final results for the TTbar analysis, so the final signal extraction is done basically fitting this boosted decision tree output shape for the two channels with some constraints to have a common cross-section for the final result. So this is shown on the left for the dilepton channel, on the right for the lepton plus jets channel. In this final signal extraction, all of the uncertainties are included, which are for the most part dominated by the statistical uncertainties. Also, in terms of the experimental systematics, there are the lepton and B tagging efficiencies, the jet energy scale, the luminosity, any possible bias due to the event selection used to build this proton mixing sample, and also the proton psi reconstruction. In addition, there are several theory uncertainties that are included, which are fairly standard related to PDFs, the parton showering, factorization and renormalization scales. And then in some of the subleading backgrounds, which are taken from Monte Carlo, there's an uncertainty on the normalization. So as you can probably infer from the plots, if you look at the simulated signal in red enhanced to a cross-section larger than expected from the standard model, we don't actually see an excess over the backgrounds in the signal-like region. So based on that, the first limits are placed on this exclusive production of top anti-quark from two photon collisions. So this is shown in the left plot with the expected and observed limit for the lepton plus jets channel, the dilepton channel, and then at the bottom, the statistical combination of both channels, which gives an observed limit of about 0.6 picobarns with an expected limit of about 1.1. So the observed is slightly better than the expected. This is mostly driven by the downward fluctuation in the lepton plus jets channel, which gives it a lower observed than expected limit. So although it's still quite far from the standard model sensitivity with only this 2017 data, this does provide the first ever limits on this type of exclusive production of top pairs. Okay, and then for the rest of the talk, I just like to mention a few of the other things that were included in parentheses in the title of the talk. So since we've done this type of search for top quark pairs and standard model processes, we can also apply similar techniques to look for a lot of other interesting high mass and beyond standard model things from two photon collisions. So one big area is looking for sort of indirect searches where you have anomalous couplings or effective field theories that give kind of a broad enhancement over the standard model. So the first of these analyses that was done was looking for this kind of light by light scattering type of process, gamma gamma to gamma gamma, which is a very simple QED process, which means it's very easy to calculate enhancements in many, if not most, beyond standard model scenarios. So this is just a list of various publications that have predicted excesses in this channel. So this is a very low background search because unlike the top quark analysis, you also have very high resolution from the reconstruction of the two photons in the central CMS detector. So again, the backgrounds here are mainly estimated with event mixing. And in this case, they use the full run-2 data set of a bit more than 100 inverse femtobarns and look for events with matching proton and photon kinematics in the green box, where they expect about 1.1 background event and observe 1 event. Okay. So in terms of what that corresponds to in constraints on the models, so CMS previously published the first limits on these 4 photon anomalous couplings using only the 2016 data, which gives you a excluded range sort of ellipse-shaped region in these zeta variables of the anomalous couplings on the right. The new limits are shown on the left using the full run-2 data set, which improve on these by almost a factor of 4. So the small box here shows what you have to zoom in on the old results to see the ellipse from the new plots. So the first results on 2016 were published in PRL this year, while the new results with the full data set were released as the first preliminary results this year. Another related process is instead of looking for production of 2 photons, we can look for production of WW or ZZ pairs, so just massive electroweak bosons instead of photons. In this case, the WW process is allowed, although small in the standard model, while the ZZ process can only happen at higher orders in the standard model, so it's essentially completely negligible. And in this analysis, again, this uses the full run-2 data set of about 100 inverse femtobars. The search is performed in the very high mass region above 1 TeV, where any standard model signal is expected to be negligible. In this case, it's possible to take advantage of the constraints from the protons to look at the W or Z decaying in the all hadronic channel, which is normally very difficult in other cases because of the resolution and the backgrounds. But in this case, we can use highly boosted W's or Z's where the 2 jets are merged into a single large radius jet reconstructed at the W or Z mass. The backgrounds, again, are estimated from data using sideband regions, various sideband regions, and event mixing also. And the analysis is performed for each year of run-2, and in this case, using events with either 1 or 2 protons used to tag the 2-photon collision. So again, in this analysis, there's no significant excesses seen above the standard model prediction. So this is shown on the top with the background prediction in red for each of the different years and final states and single or double proton tagging. The blue dashed line shows what an expected signal would be for a kind of reasonable anomalous coupling signal that would enhance the WW in this particular case, and the black points show what's observed in the data. So based on this, it's possible to again set limits both on the cross sections and on the anomalous quartic gauge couplings of photons with W's or Z's in several different scenarios of dimension 6 or dimension 8 with different unitarization schemes. In terms of how this compares to similar results, so there's various subtleties comparing these depending on which anomalous coupling scheme you use and which unitarization scheme you use. At least in terms of the most direct comparison to the run-1 results that were done without proton tagging in a similar channel. So this is on the right, the summary plot showing both the CMS and Atlas results. And on the left is the new results using the full run-2 data set. So again, it significantly shrinks the area of this allowed ellipse for anomalous couplings using these 2 photon collisions with tagged protons. Okay, and then just for the final topic, I'd like to mention a couple of things on more direct searches done at CMS by colliding photons recently. So basically the idea is that if there's some beyond standard model physics that's light enough, then it's possible that instead of non-resonant enhancements, we could actually directly produce new particles in these types of processes that could be seen both in the central detectors and by using the tagged protons. Now, in most cases, of course, there are a huge number of previous LHC searches that very strongly constrain all of the models and make this probably not feasible to see in this type of mode. So the idea is more to focus on some scenarios where there are certain loopholes where things may not have been seen in other searches. So especially either invisible or difficult to reconstruct particles that can be detected thanks to the closure of the kinematics from the protons, or especially particles that have very large couplings to photons. So one example of this that's been released this year was a search for so-called missing mass in the Z plus X or photon plus X spectrum. So the idea here is to try to reconstruct a Z plus 2 protons or a photon plus 2 protons. Assume these all come from the same collision and look if there's anything left over from the total 13 TeV collision energy. So if you're familiar with E plus E minus colliders, this is in some ways analogous to a kind of recoil analysis done in E colliders, although normally in hadron colliders, we only look at the missing transverse energy, say, so this is the, as far as we know, again, the first use of really looking for a missing invariant mass at a hadron collider. And so the important thing to point out is that there's no assumption made on what the X is here. So it could be any new particle, including things that are invisible or long-lived or otherwise difficult to reconstruct. So this analysis again uses 2017 data. Again, it does the analysis split into many different categories by the final state, so Z to mu mu, Z to E, or photons. It also uses a couple of different proton reconstruction algorithms, and again tries to determine the backgrounds from a combination of event mixing and control regions, like looking at electron and muon events. So this is just shown in the plots on the right. So the background prediction in gray, the black points are the data, and the open red histogram shows the an expected signal you would see for some assumed cross-section of this invisible X particle. So again, in this analysis, they do not see any excess over the background predictions. So this allows placing limits on the associated production of these unknown X particles, varying from about 50 femtobarns in the C plus X case to about 1 picobarn in the photon plus X case. So this is done in the region from about 600 GeV up to 1.6 TeV, and in general with very high resolution on the missing mass due to the proton reconstruction. Just to mention, the main reason the photon plus X limits are weaker is due to the trigger, which was pre-scaled in this data set, so corresponds to a smaller integrated luminosity. Currently, this is using only about 1/3 of the available data with proton tagging in run 2, and has not yet tried to exploit timing detectors, which could also help to suppress the background. So there is still some room for possibly interesting improvements in the run 2 data as well as in run 3. And then the final topic I'd like to mention on these direct searches is looking for Axion-like particles. So I think last time there was a similar seminar at LIP, there was a specific question about using this to look for Axion-like particles. So finally, we have some results to show on this. So the initial idea with axions were conceived as a very light particle to try to solve the strong CP problem in QCD and possibly also provide a dark matter candidate. Obviously, in this kind of analysis at the LHC, we can't look for KeV particles or extremely light things, but there has been quite some recent interest in looking for heavier axion-like particles, which could appear at very high masses, which we're sensitive to. So this is essentially an extension of the gamma-gamma to gamma-gamma anomalous couplings analysis, except looking for a narrow resonance instead of a broad excess. Just to mention, for historical interest for people who have been around a while, you might remember at the very beginning of the LHC run 2, both Atlas and CMS had seen some possible hint of an excess at around 750 GeV decaying to 2 photons in 2015. Finally, this wasn't confirmed in the rest of the LHC run 2 data, but it generated quite a large amount of interest in this idea of looking also in 2 photon collisions, where this would be kind of a golden channel to study if there was some new particle at this mass range, it could be detected both in 2-photon production and decay to photons. So this reinterpretation of the anomalous couplings analysis was done with the signal modeled as a narrow resonance. So this is just showing on the right the simulated signal for several different assumed Axion-like particle masses. So in general, we expect very narrow signals. Again, since no excess is seen, this is used to place new limits on the plane of the mass and coupling of these Axion-like particles from about 600 GeV up to almost 2 TeV, shown on the left. And just to point out that the best sensitivity actually comes very close to this 750 GeV, where there was some hint at the beginning of run 2, but again, there's no excess seen here in the 2-photon production data. And just to point out that this is actually interesting in terms of the overall picture on Axion. So this is a plot from a few years ago, I believe by Atlas, showing some of the existing constraints on axions and axion-like particles. So the notable thing here is that if you look at the green and the blue, the best limits are actually coming from gamma-gamma to gamma-gamma in LHC heavy ion collisions. So going from a few GeV up to almost 100 GeV. But above that, the sensitivity from the heavy ion analysis starts to fall off. So if you then also add in this proton-proton analysis using the tag for protons, you're covering really a much higher range that is completely complementary to the heavy ion limits and provides very strong limits on axion-like particles at this very high TeV scale. All right, so I think that's the last of the recent results from this year that I wanted to discuss on production from 2 photons in CMS. So just to summarize, there was a first search performed for top quark pair production from 2-photon interactions using about 30 inverse femtobarns in both the lepton and lepton plus jets channel. No excess was seen in either channel, and so the very first limits on the cross-section for this process were set. And this, of course, builds on a lot of previous work to verify all the standard model signals for these very high energy 2-photon interactions. Then similar approaches were extended to probe beyond standard model physics in a number of other final states from 2-photon collisions. So in terms of the indirect searches, this provides the first and best collider limits on the anomalous 4-photon quartic couplings. It's provided new constraints on anomalous gamma-gamma WW and gamma-gamma ZZ quartic couplings. In the area of direct searches, this has been used to perform the first missing mass search for new resonances at a hadron collider in Z plus X and gamma plus X, and what appear to be the best limits on axion-like particles from gamma-gamma to gamma-gamma at the TeV scale. And so finally, for the outlook, just to say, I hope I convinced you that the LHC is likely to be the best and definitely the cheapest, very high energy photon collider that will be available for a long time. So it's important to try to exploit this mode of operation as much as possible to study both standard model and beyond standard model physics in this new type of operation. So there is still a lot to do with the large run 2 data sample collected in proton-proton collisions, as well as the new run 3 data that's now being collected since a couple of months ago. And also for time, I did not mention anything really about the heavy ion 2-photon physics program, but there's a lot of very interesting stuff going on there as well, both in standard model and BSM physics. So with that, I think I'm at the end. So thank you.
Thank you, Jonathan. Well, thank you very much for this very nice overview of the recent results by CMS. I'm glad that you included other things in your title.